What is up, people? This is Hudson McNutt. Welcome back to Learning with Hudson. It's going to be a good time today. Today, we're going to talk a little bit about magnets, about Mars, and kind of to integrate some of these principles more in depth. We'll apply them to the fictional or not so fictional story of The Martian, the book, The Martian, or if you've seen the movie, The Martian with Matt Damon. If you're into that, then this is the video for you to be watching right now. This is good stuff. But before we talk about Mars, we're gonna have to talk about Earth a little bit, kind of set the stage, and then talk about the sun for a little bit, and then we'll get down into the nitty gritty of Mars. So first, Earth does have a magnetic field. In case you were unaware of that, we do have a magnetic field. Um, And so there's a north and a south pole. If you're unaware, there is, right? And there's also so there's a geographical north and south pole, and there's also a magnetic north and south pole. And so the magnetic north pole is actually geographic south, and the magnetic south pole is actually geographic north. I know that's kind of confusing, but in the beginning, when they were naming stuff and they had the compass, you got a guy just chilling right here on Earth, and he has a compass, right? And it was pointing to what he would call north, right? So he's like, oh, that's north, right? But in reality, the compass was pointing that way because of magnetism and opposites attract. So it was actually attracting to the south pole, the magnetic south pole, but they call it geographic north. So that can be kind of confusing sometimes for people, but hey, that's how it is. Um, and that also won't be like a problem forever because actually every couple 100,000 years, the Earth's poles actually reverse, um, which can be helpful for certain things, which we'll talk about a little bit later. Um, but a key thing to recognize. Let's get rid of this guy real quick. See ya. A key thing to recognize is how the Earth has a magnetic field. So the Earth has a magnetic field because its core is molten iron, right? And if you didn't know this about magnets, you're going to learn. We'll do a quick refresher course. Magnets, to be a magnet, you have to have a current, right? So these this iron, this molten iron, is kind of churning around in the middle of the Earth, and that allows for the magnetic field to exhibit itself around the Earth. This is the magnetic field, right? And so this churning current of molten iron in the core is what gives the Earth a magnetic field, right? And so it's as if there's just like this giant bar magnet just chilling in the middle of the Earth, right? With a south and a north pole, right? And then it's tilted about 11 degrees off the axis. I mean, 11 degrees, right? Which kind of adds more attributes to the magnetic field, right? So the bar does move slowly, but like super slowly. So the poles are moving super slow, but it's not enough to mess with compasses or anything. So for the most part, that's not important. Um, and a key principle we want to take away from this slide is the fact that the magnetic field expands so far out into the atmosphere. That's a very important attribute that we're going to need to pay attention to for the future. So to set the stage for kind of how powerful the Earth's magnetic field is, it's kind of varies between 25,000 and 65,000 nanoteslas, and you're like, whoa, wow, that's like a lot of nanoteslas, right? But I'm sure you've all experienced that when you like go outside, metal doesn't just like stick to the ground and you can't like pull it off, right? So as like a way of reference, like a refrigerator magnet is like 10 million nanoteslas. So we don't really feel the strength per se of the Earth's magnetic field, but it expands really far out. Remember, I said that last slide. It expands really far around the atmosphere, which is what is really important. So yeah, the next point we need to remember is this phenomena called solar winds, or as we can call it, space radiation. So the sun is really hot, as we know, right? And the sun's core, right in here, in the core of the sun, is extra, 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 extra hot. It's just crazy hot. And the sun also exhibits some magnetic fields that like come off the surface of it, right? And you see these kind of little circle things coming out. They're really strong magnetic fields, and when they clash, so if they like cross over each other, they send out these really high energy particles into the solar system, right? And it's not like they travel like a couple hundred miles, like they travel throughout the entire solar system, right? Like some of these particles, some of these loops are just like so huge that they just go around the Earth. Like this is Earth, and like the Earth doesn't even like experience them because they're just so huge, right? So they're traveling at these insane speeds, right? So fast, and like they can be like really dangerous. It's actually one of like the major concerns that astronauts experience when they travel in space, are these solar winds, because they can penetrate through spacecraft, and it's like a really big deal, right? So yeah, solar winds are pretty brutal, honestly. They cause a lot of damage in the solar system. So you might be asking, Hudson, why do I care about solar winds and the Earth and magnets? I thought we were going to talk about magnets and Mars, right? Well, let me tell you why this is important. So magnets on Earth can be useful, one for compasses, right? I talked about the reversal of poles, which can make it helpful to date things, right? If you've got a reverse in the poles, then it'll be easier to date like fossils and stuff like that, because the Earth is pretty old, right? But like we said, this is super key right here. The magnetosphere of the Earth extends so high that it actually protects from the solar winds. So remember, these solar winds are blasting these particles at the Earth. I think this is a moon, but the picture is really good for this. So pretend this is the Earth. It's blasting these particles at the Earth, right? And these particles are such high energy, and they're traveling so fast that if we didn't have the magnetosphere around us to block these particles, they would just blast away the atmosphere, and we would pretty much die. We would actually look a lot like Mars. Earth would be like Mars. It'd be really like cold. It wouldn't be as cold because it's closer to the sun, but it'd be really cold, and there'd be no atmosphere, and it would just be a pretty awful situation if it did not have its magnetic field, right? I know some of you are thinking, but I'm pretty sure there's magnetism on Mars, right? That is true. There is magnetism on Mars, but it's a different like kind of type of magnetism than the magnetism on Earth. So the magnetism on Earth, remember, it's like in the core, right? Got your bar magnet. It's in the core and extends out. This is Earth. But on Mars, they're just kind of like on the surface, little pockets, right? Little pockets of magnetism, which helps with the ionosphere. These are called crustal magnetic fields. So they help with the ionosphere and stuff, but they're not strong enough, and it's not just a singular like bar magnet in the core, right? So Mars doesn't have its atmosphere, right? These remnants, these little circles I put in this picture here of some of the magnetism where it's stronger and where it's weaker on Mars. So some of the remnants come from the earlier days of Mars when it did have a magnetic field that was produced by the core, right? And then, so when an asteroid or something lands in here, and it lands, right? All this molten like rock and stuff is on the ground and on the Earth, right? And so it's pretty much melting and then it's cooling. So if you cool down a metal above its Curie temperature, then it actually gains magnetic properties if you do so within a magnetic field, right? So it has all these magnetic properties because there was a magnetosphere at some point on Mars. But as we can see, for example, if you see this giant crater zone right here, it's called Hellas. So Hellas was a giant asteroid, right? And it hits this point right here, boom, leaves a giant crater, but it leaves no magnetic properties within, which is weird because if it's molten like iron or material, and it cools down from its Curie temperature, then it should have magnetic properties, but it didn't. So about 4 billion years ago, the magnetic field of Mars just kind of vanished. And we don't really know why, to be completely honest. So, comparing Earth with Mars, Earth is suitable for life and water, and Mars is not. Right? So Mars used to theoretically be able to sustain life because we know it has oceans and and it had an atmosphere because those are now frozen, right, at the peaks up here, at the polar ice caps. But when the magnetic field disappeared, the solar winds had access to Mars' atmosphere. And so we talked about how powerful they were, and they literally just blew away the atmosphere of Mars. This just was gone forever. And so although it does potentially have a molten core, kind of depends on who you ask. Some people think it does, and some people think it doesn't. It does not have a strong magnetic field that extends all the way out and around it. And so this is why Mars is so cold, because it doesn't have an atmosphere, right? Which makes it not sustainable, especially for the Martian, right? So the question becomes, if we were Martians and we were living on Mars, what would we do? Like, because we want to live, right? We want to breathe. We want to not freeze to death, right? So you've got Mars out here. You've got the sun chilling out here, just bombarding us with all these horrible solar winds, right? So what do we do? What's the solution to this problem? Well, first off, you could destroy the sun, just exit out, right? Then you don't have any more solar winds. But that doesn't seem like a very good option because the sun does a lot of good as well as a lot of bad. So that's not an option. The second option is you could create a magnetosphere around Mars somehow that would deflect the solar winds away from Mars. And that would protect Mars from the solar winds. If you can protect Mars from the solar winds, that can warm up the planet and it can melt the polar ice caps, right? It would actually, theoretically, from some of the studies they've done, it would increase the temperature by about 4 degrees Celsius, which would theoretically be warm enough to melt the polar ice caps, releasing CO2 and water into the atmosphere around Mars, creating kind of this greenhouse effect, which would then be protected by the magnetic field. And so over time, Mars would return to its previously potentially habitable state. So if we could somehow create a giant bar magnet, if Matt Damon could create a giant bar magnet and place it in the middle of Mars and create a giant magnetosphere around the planet of Mars, he could really, in reality, make it habitable, right? So there are theoretically possible solutions to living on Mars, which is why people are still investigating it and you hear about people researching it and stuff, right? So magnets and the magnetic field on Earth are way more important than we think they are. And they really do provide protection from the sun and protects our atmosphere, which is why the Martian needs a magnetosphere to survive. And that's why Earth has one and we all live here. So thanks for listening, guys. Hopefully you learned something and hopefully we get to Mars someday. Appreciate you taking the time to check in and we'll see you guys later. Thanks. Bye.